Hi, I'm Bijou Smith, or A Chronon Master. It's my other handle. I do some NCEA tutoring, and these are exam practices. The purpose is to show you that it takes a long time to do these exams, even for an expert like myself. For the complex algebra topic, this particular one, this will be the first in the series that I do for 2022. I haven't done any complex algebra tutoring for like years and years. I used to do statistics. In the last few years tutoring, I haven't had any students doing the 91577 standard. So this will be really interesting because it might be quite close to how a student would do it in real time if they had no stress. And the point of this is you can copy this video and send it to people at the Ministry of Education, if you like, or the NZQA, and show them that they've really got to give students more time for exams. If you have 3 hours and it like takes to do 3 standards, if I take 1.5, 1.5 hours to do each paper, then you're gonna have to say that you should be allowing students 5.5, 6 hours, I reckon, 6 hours to do these exams stress-free. And so that's a little something to keep in mind. It's my little political statement to the NZQA and schools. If you're going to give students this many questions, you better give them 6 hours. But let's see, maybe it'll take me only 1 hour to do this, maybe it'll take me 2 hours, in which case you should give these students 6.5 hours or something like that to do these exams stress-free. The purpose of the NCEA is not really to test students under stress. You've got enough anxiety and stress already because you're testing the student. Instead of doing what you should be doing, which is testing the school, you should test the school. And then the schools that are not performing should get more resources so that they can perform better. But anyway, that's enough of the politics. You're welcome to use this example practice session in any way you like. So the thing is, I also like this will be a good one to follow because I'll probably make a lot of mistakes, and that's sort of usual. I may make even more mistakes than some typical students. And so that's just to show you what to be realistic about these NCEA exams. Okay, so got to get in the head of like complex numbers. We're trying to think of this as a problem where you've got an a plus ib, well, so something over a plus ib, and you want to convert that to a number a plus ib without having a fractional part, right? So the technique for doing that is to multiply by the conjugate. A conjugate of a complex number is it's just its reflection in the real axis. So it's actually a mirror reflection. It's conjugation, particular mirror reflection with the real axis as the line. So you can do that for these what's called surds as well. It works in a similar way. So I would write it as 1 plus the root of 5 times 1 minus the square root of 5. It's the conjugate. But to keep it algebraic equals, we have to multiply by 1. So you multiply the whole thing by 1. Okay, so then we get 12k minus 12k times the square root of 5. That's because we want to split it into 2 pieces, right? On the numerator, and then on the denominator, it's like a difference of 2 squares. So it'll be 1 squared minus the square root of 5 squared. So it'll be 1 minus 5, which is negative 4. So it'll be negative. Okay, so that just goes to negative 4, and then we have 12 divided by 4, negative 3, and it showed it told us not to factorize, not to bother factorizing. So it'll be that, and then there's a negative 4 again, but negative 12, so positive 3. Okay, screw 5. All right. Already I'm over time compared to most advanced students. All right, well, cis is cos plus I sine. Right. It's also the same as doing an exponentiation of the number theta in here. Now, polar form is r e to the I theta. Okay, r e to the I theta is polar form. I'm thinking. So if u is that, or u over v. Radio. So it's already sort of in polar form. We've got e to the I pi over 3 divided by m squared e to the I pi over 5. Okay, so that'll be the m's are just scalars. So okay, so u over v equals that, and so we get m cubed, and then we multiply by the conjugate. Well, the conjugate of z, say that's equal to z, is just the negative on the angle. That, again, that's the same as a reflection in the real axis. If you take theta there and you take minus theta, you get the conjugate complex number, z conjugate. All right, so we multiply above and below by the conjugate of the denominator, minus I pi over 5. And then, okay, so that's just e to the I pi over 5, e to the minus I pi over 5. Okay, but those two are going to cancel together, right? So we get m cubed e to the I pi over 3 minus pi over 5. Now on the bottom it's just e to the 0, which is just 1. And so it's going to be, well, what's 1 over 3rd minus 1 over 5th, right? It's cross multiply, so it's 5 minus 3 over 15. 2 over 15, so it'll be m cubed e to the I to pi over 15. Okay. Okay, so the argument, so u equals ru e to the I theta u, right? V equals rv e to the I theta v, and w equals rw, the magnitude of w, e to the I theta of w. And so when you do UVW, you get U RV RW e to the I theta u plus theta v plus theta w, right? Heck, we're gonna have to work out the arguments, right? So just trying to think about what the easiest way to do it is. Since I guess they don't tell us whether the k is positive or negative. So if we have a real part, call it x, and the imaginary part, call it y, like that, then the argument is going to be equal to the inverse tan of y over x. Okay. So theta u is going to be equal to inverse tangent of 2 over 3 and theta v is going to be inverse tangent of 2 of half, and theta w is going to be inverse tangent of k over 2, right? It's up to some maybe signs if your angles are greater than 90 or what have you. But let's just do this in the simple way possible, because they're going to add up to pi over 4 in any case, right? Now, this is where you might think about, I don't know, changing your calculator from mode degrees to radians, so that you get the pi and angles in radians coming out. Sorry. And I'm going to use my Python calculator here for this. Well, so let's see if that's a wow, I don't recognize that. What's the square root? I'm not recognizing any of these. Well, just trying to think if it's a nice number. Could use symmetry cosine and do like theta as the inverse cosine of x over the magnitude. So for example, okay, let's do the first one again. That's the actual angle in radians, but it should also be the inverse cosine of the x component over the magnitude. So it'll be 2 squared. Sorry, x component would be 3, and then you get a 9 plus 4. That's a 13, right? So it's probably the square root of 13 that I'm looking at, right? So at this point, I'm thinking I don't really know any shortcuts for pi over 3, pi over 4. They usually involve 3 halves, square roots of 2, and all that sort of thing. What do I have here? Yeah, so that would be a half. Oh no, what is it? 2 over 3. V was half. Write that out, sorry. Okay, so from here I just plug it into my calculator, right? So I would go, well, just, add them all up. 2 over 3 half, and because k only appears in one of them, we've got a chance of solving it. All right, so just plug this in the calculator. Subtract those two, and then k would just be twice the tangent of pi over 4 minus the rest. You have to copy all that down, right? Cut and paste. Okay, do that. Sorry. A tan as inverse tangent in my Python console here. Okay. If I had a lot of time, I'd come back and check this 5, 4, 5, 4, 5. We can write that exactly as that recurring. Looks like anyway, close enough. So what you could do is actually, what the heck, let me show you how to do it. What you do is you download free software, Maxima. Let me show you Scratch. So it's just like GNU Linux would be sudo app install Maxima. That's all you have to do. Run the thing. Calculate U, V, and W. So it'll be, you don't do equals at this. To assign to a symbol U, you use a colon for some reason. Maxima knows about complex numbers, but it's percentage I. And I think you can do semicolon to just separate out commands. 4 plus 2 times I, and UVW. What is it? 2 plus K times I. 2 plus K times I. But at the beginning, maybe we want to define K. Yeah, so just do a few of those. And then define a new symbol, UVW, just equal to U times V times W. What is it? And then I think in Maxima, definitions for complex functions for complex numbers. Real part, polar form, image part, conjugate, C-arg returns that. Complex argument. That means the sort of angle of the complex number. So I think I can just do this. UVW. Oh yeah. I want that as a floating point number. Okay, and then compare that to pi over 4. Oh, but as a floating point number. Just so I can check the decimals. Oh, what? Oh yeah, percentage pi. 7/8. Sweet. Works out. At least to a few decimal places. Remember, for K, I didn't. For K, I just did a few. I didn't do too many of them. So there's obviously going to be an error at the 10th decimal place or something like that. I don't know if you can easily do that check on your calculator. If your calculator does complex numbers, you could do it, right? Just multiply these three together and then check the polar form of it. If you got that on your calculator, it should have rectangular to polar. Most calculators these days could do that. This smells like smells like a quadratic. 2 solutions, right? And you want to look at the discriminant, b squared minus 4ac. For one real solution, we want that to be 0. Set that to 0. But we've got to find the quadratic. So you might think of squaring this, but if you square that, the middle term is going to still have a square root. So you don't want to square that. To get rid of the square root, I guess we've got some space here, so I'll just go for it. We want to take the x off the other side. Well, I should just take that over that side, this over that side. How about that? So it'd just be x minus 5. And then you square both sides. So you get 4x plus p equals, now squaring this, you get an x squared minus 10x plus a 25. Yeah, so we gather terms, so we get x squared. Now from here we get 4x, but on the other side it's negative, so minus 16x, I guess. And then on the side we get plus 25, but then minus 4p equals 0. So that's our a, b, and c in the formula for the quadratics. So the two roots, so negative b is 16. Sorry, we just want to find out, just want the discriminant. So b squared, 16 squared minus 4, a is 1, c is 25 minus 4p. Okay. Wait a minute, did I make a mistake here? I'll take the x over that side, it's plus 5. So plus 10. 10x minus 4x. I was just thinking this is 16 is a bit big. That's my clue that I made a mistake. It was just random that I thought about that. So it'd be 10 minus 4, so plus 6x, right? Okay, so b is 6, so 36 b squared minus 4 a, c, a is 1, c is 24 minus 4p. Set that to 0 for one root. And we get, whipping that on the other side, it'll be 24p equals 36 over 4. That's, what's that, 18, is it 9? Right. So swap sides again, p on that side, 25 minus 9. That'll be 16, right? So 16 over divided by 4, p is equal to 4. Moving on, yeah. Conjugates and things. So if you got a complex number x plus iy, then its conjugate is just obtained by alternating the sign of the imaginary part. Yeah, and the modulus of a complex number is defined to be the product of its self with its conjugate, square rooted actually, so we should square that. That's really the definition, and that would be well, let's write it out just in case you forgot. You wouldn't do this in the exam. That's the difference of two squares, but the difference of the square, so it's a squared minus y squared, and that squares to negative 1, so the negative becomes a difference of two squares becomes the sum of the squares when we have the unit imaginary. Okay, so real parts. Yeah, so let me do the real parts too. So we have phi, or a complex number, and let's just call it a plus b. Oh no, it doesn't. Well, it doesn't matter. It doesn't matter what I call it. X and y are fine. Then put that underneath it, and you notice what you can do is add these together, and the imaginary parts cancel, but you get double the real part, 2 times the real part. Whereas if you subtract the conjugate, then the x's cancel, the y's add up, and you get 2i times the imaginary part of the number. So we'll use that later, but the idea of this is at least you start working from one side and try to get to the other side. So we'll start with the left hand side. Okay, so what is this? It's w plus z is the whole thing. So we want to square it. We can use this result here, up here. Okay, so we can just, the modulus squared will just be that, plus the complex conjugate of the whole thing, minus, now do the same thing here. Since it's a modulus squared again, we just complex conjugate of the whole thing. Okay, now I guess there's another result here, which is that complex conjugate of a sum is the sum of the complex conjugates. I guess it's the other. It doesn't matter. The order doesn't matter because these are commutative under addition. But anyway, now you don't have to prove that, I don't think. Just use it as background knowledge in your exam. So we'll have w plus z, w bar plus z bar. By that I mean conjugate. W minus z conjugate, and then w conjugate minus z conjugate conjugate. So here's another result. The conjugate of a complex number is just the complex number. All you do is you go from plus I to minus I back to plus I if you do double conjugate. Right. So that will be, let's expand this then. So it's w times w conjugate plus w times z conjugate plus z times w conjugate, and the other bracket will be w times w conjugate minus w times z, remember, minus w conjugate z conjugate plus z conjugate. Okay. Okay, well that cancels that. Any other cancellation? Did I miss something out? Oh yeah. So that still cancels there, but I forgot the last term, which was this z conjugate. And that there's a negative sign on this one, right, from the one out the front, so those will cancel out as well. Okay, then you do the thing where you want to factorize. You just look at least for pairs of numbers that'll factorize. So those two, you get a w times a z plus a z conjugate, plus because there's a double negative here. And then the other one looks like there's a w conjugate in common. So pull that out, and you get left with z, a double negative again, so it's plus. Right. So these were just our background results. So from the background results, remember a number, complex number plus its conjugate is twice the real part. So this will be, first of all, these are the same. So we can factorize further. And these are both complex number plus its conjugate, so they're both 2 times the real parts. Which equals 4 times the product of the real parts of each. Lo and behold, that's equal to the right hand side. That's what we wanted to prove. This square symbol also means quo erat demonstratum, which is what we wanted to prove, roughly translated from Latin. So we're done. Divide. Oh no. Division, long division. Let me. Where am I going to do this? Where am I going to find the room to do this? I think I'm going to have to draw a line down. So x plus 2 divided into cube minus 3x squared plus bx plus 9. Damn. Remember, the long division of polynomials is the same as long division of decimal numbers. Instead of x, you could just have a 10. So you got thousands, hundreds, tens, and ones. Same thing. But anyway, so first of all, x goes into x cubed, x squared times, and you get 1x squared will do it, will do the job, which means we get an x squared plus a 2x squared. Subtract these, sorry, cubed, and then you get negative 3 minus 2, so that's negative 5x squared plus bx plus 9. Okay, then x goes into 5x squared minus 5x times. We get a minus 5x squared, and then a minus 10x here. Try to keep your columns lined up. Subtract those, so you get 9. B plus 10, right? Is that right? Yeah. B plus 10x. Is that it? Okay, so we can do one more, right? B plus 10. So we get B plus 10x plus 2 times B plus 10. And then subtract, so we get 9 minus, expanding out to the left hand side here, is our equals the remainder. I knew I'd have run out of space for that. I'm not sure if this is how they teach it at school these days, but that's the only way I could think of doing that. Yeah, so therefore 3, the remainder, must be equal to 9 minus 2 b plus 10, I guess. Okay, so that means 2b plus 10 must be equal to 9 minus 3, 6. B plus 10 equals 3. So b equals 3 minus 10, negative 7, I guess. I'm not really sure if that's correct, but you can check my working. If you don't agree, let me know in the comments below. Probably, I must have made a mistake there somewhere. Although, I don't know if Maxima can do this. I think there's a simplify or expand function. See what it gives. Let's call it. Let's give it a name for like fraction or quotient. Maybe expand. a simple way to test this. I think it's called radcan or something. Functions for simplifications. Okay, maybe that's what I want, radcan. Why is it called radcan? Yeah, anyway, let's give up on that. It's got to be a simple way to test it, but I'm not going to bother. Find the complex number z. Oh yeah, so wait a minute. What does it mean? It means that x plus 2 times this must be equal to that. Minus 5x plus b plus 10. Okay, let's make b negative 7 for a start. B plus 10. Let's write that as p, say. Expand p. Do the remainder. What is it? 9 minus 2 times b plus 10. It'd be 3, right? And 6 b 7 6 9. Is that right? 6 plus remainder 3 is 9. Yeah, that looks about right. Must be right. Okay. Got to find z here. Okay, when you got these in conjugation, this usually means you want to use the rectangular form. So you just say let z equals x plus iy, and then you try to find some equations that will solve for x and y. Simultaneous equations, because there's two unknowns here. Alright, so we've got x plus iy equals, plus 4 times the conjugate of that, so x minus iy equals 15 plus 12i. Now, because real and imaginary parts of complex numbers are kind of orthogonal, because that's what they are, right? Imaginary part, real part. It's like a two-dimensional calculus, geometric algebra, really. In fact, you should use geometric algebra instead of complex numbers. Complex numbers are kind of old-fashioned. I don't use complex numbers anymore. I use Clifford algebra. That's a little political statement there to anyone listening from the education establishment. Anyway, so we want to gather the real and imaginary parts. So we've got x and 4x, so that's 5x. We've got 1 iy and negative 4 iy, so that's negative 3 iy. Which means that 5x has got to be 15, just as looking at the real parts, which means x equals 3. And looking at the imaginary parts, it means minus 3y has to be equal to 12, right? So y is equal to negative 4. I've got a cubic. That's annoying. One of the solutions is 4. Okay, so that means it must factorize plus 4, remember, minus the root. Z minus negative 4, if you like. And the rest has got to be a quadratic. And we'll imagine that these could be imaginary numbers or complex numbers. Yeah, well, so we can completely factorize any polynomial if we know, if we are allowed to use complex numbers. So it'll be like Z minus R plus and Z minus R minus. These will be the two, those will be conjugate roots. I think that's how to do it. Well, maybe before that I might actually just find A, B, and C. How about that? So that'll be AZ cubed. Let's in fact not expand it right there. Let's just look at each power separately. So Z cubed, I've got A only on the left hand side, and that has to be equal to 1. Okay, so A equals 1 straight up. Let's look at Z squareds. We've got 4 times A, and then you get a Z squared from these two here, so plus B. And that's got to be equal to this guy here, minus 2. But A is equal to 1, so we can immediately figure out that B is equal to negative 2 minus 4. Okay, negative 6. Terms in Z, we've got 4 times B from that, and we've got C times Z from that, so C, that's got to be equal to H, but we don't know C yet, so that just means that H equals, well, B was 6, so 4 times 6 is 24, negative 24, C minus 24, right? And then the constant terms, we've got 4C has to be equal to 180. Yeah. So C is got to be equal to 180 divided by 4. Well, divided by 2 is 90. So divided by 2 again, 45. Okay, so that means H is equal to 45 minus 24. What's that? 15 and 6, 21, is it? 21 plus 20. Yeah. Now, what are the other solutions? Right, so the second factor factorizes further. How should I do this? Forget it. Let's just use the formula for quadratics, right? To find a root, we've got to make it 0, so it's going to be, A is 1, right? So it's Z squared minus 6Z plus 21, I think. And so there are two solutions. That's A, B, C. So negative B plus or minus square root B squared is 36. 4A is 1, C is 21. 4 times 21. Let me save space. Divide by 2A, which is just 2. So 6 over 2 is 3, plus or minus. Now what's that? 36 minus 4 times 21. 36 minus 84. I don't know. Sounds okay to me. Minus 48. So we've got square root of 48 over 2. Of course, that can be written as the square root of 4 times something, probably. 4 times 12 over 2, right? And then we can take the 4 out the side by doing a square root of it. So it's 3 plus or minus, and then it'll cancel. Sorry, made a big mistake there. Negative 48. But we can square root the negative, it's just I, so bring that outside the square root. What we got left with then is the square root of 12. That's the two solutions. So A is equal to 3. Yeah, I think, wait a minute, negative 2. I don't know. Yeah, I think A is, did I get a minus sign wrong there? I may have got a minus sign wrong. But anyway, A I think is 3 and B is the square root of 12, I would say. I have to check it. Don't have time to check it, so I'm going to keep moving on. Ooh. What's the relation here? Here's the Z. Okay, so I'd say W equals 4 over 1 minus the square root of 3i minus 2. But I want to get rid of that in the denominator, so I multiply by its conjugate. Upstairs and downstairs, so it's just the same as multiplying by 1. So we're not changing anything. Alright, so upstairs I've got 4 plus 4 times the square root of 3i. And downstairs it's just the difference of two squares, which becomes the sum of the squares because of the I, when the I gets squared. So you get 1 plus 3. Okay, so it's equal to 4 over 4 is 1. And then again you get 4 over 4 is 1. Okay, so W equals negative 1 plus the square root of 3i. Okay, now this is tricky. It's like a, I know this triangle, right? I know a 1, a 2, and a square root of 3 like that, and that's pi over 3, 60 degrees. This is pi over 6 up here. But that would sort of suggest that the angle is equal to pi over 3, but it's going to be negative. So if you put that into your calculator, it's inverse tangent of the vertical divided by the horizontal. If you put that in the calculator, you probably won't get pi over 3. So what we should do is we should respect the geometry. This means that in the complex plane we are at negative 1, but square root of 3i, which is up here somewhere, so that's the W there. Okay, whereas this one here, we were in this particular quadrant here, but we're not there, we're in this quadrant here, the second, called the second quadrant. 1, 2, 3, 4. So the angle, if this is pi over 3 here from the geometry, 1, 2, square root of 3, negative 1 really, then this angle, the actual angle conventionally defined from the real axis counterclockwise will be pi 180 degrees, in other words minus pi over 3. Okay, pi minus pi over 3, which is 3 minus 1, 2 pi over 3. Okay, so that's the argument of W in radians. if you actually do this on your calculator, don't forget to put the negative, and don't forget to convert to radians from degrees. I don't like these low-key problems. I can stare at this all day and have no idea that it's a circle. But this looks like a circle. But anyway, we can just do it algebraically. So again, the clue is the x and the y here, so we let z equal x plus iy. Okay, then the locus condition is the absolute value of z plus I, so that would be the absolute value of x plus I, y plus I is 2 times x plus I, y plus minus 5i. Okay, and so that would be, you could say x plus y plus 1 times I equals 2x plus y minus 5i. Now remember, modulus of a complex number squared is equal to the complex number times its conjugate. So what we want to do is square it, both sides. Y plus 1 4. We've got to square everything. But now we can use this formula, so we can go, that's equal to x plus y plus 1 times I times the conjugate of that minus y plus 1 times I. Good. Okay, but we know the result. This is just going to be the absolute value of the thing, the sum of the squares of the real and imaginary part. The other side, for similar thing, x squared plus y minus 5 squared. And we could have probably gone straight from here to here if you wanted to. Anyway, expand. Thing is, we don't have a y minus anything here. It's 2 different y's brackets, so we've got to get rid of those. 2y plus 1 there. 4x squared. This will give you a 4y squared. It'll also give you a negative 10y times 4, so minus 40y. And then I'll give you a 25 times 4, which is 100. And then, what are we trying to do? X squared minus blah blah blah. I guess I'll chuck everything onto I reverse the order, I think. So on the right hand side, I subtract x squared, but I'll move it all over to the left hand side. Hopefully this doesn't confuse you. And then so do the same thing. So 4y squared minus y squared, so plus 3y squared. And then minus 40y minus 2y. I think so. That's a big number. 42 minus 42y equals, now on the other side I had a 1, so I'm going to subtract 100 from it, so it'll be negative 99 on that side. That's really crazy. Is k going to be complex? Yeah, that's a bit of it. I don't know. You see what I did there? I wanted to leave just the constants on this side, so I've got to take the 100 over that side, so I've got to subtract the 100. Yeah, anyway, divide by 3 both sides, right? .42 I think must divide by 3, surely. 42 by 3. Yeah, 14. Alright, good. Now we want to do it like this. We need to complete the square. Complete the square. So well, we've got x is fine. It just means a is equal to 0. Up here, a is equal to 0. To complete the square, you halve the coefficient of the linear term. So it'll be 7. And then you add on the correction. So we would have plus 49 coming from this expanded. So we're going to subtract 49 to correct for that. But look at this, it's not going to make the 99 positive at all. So we get x minus 0 squared plus y minus 7 squared. So b is equal to 7 and k is equal to negative 99 plus 49, right? So that's I guess negative 50, right? So a equals 0, b equals 7, and k equals, k squared equals negative 50, so k equals I times the square root of 50. I might have made a mistake somewhere in there, but you're welcome to check it and fix my working. V2R minus S, find V and mark it on the diagram. That's question A. So R is 3, 2, and S is 2 minus 5i. So V is 2r minus 2 plus 5i. That's negative s. I guess that's 6 plus 4i minus 2 plus 5i. I guess I should have written it like that, really. Show you my thinking. Gather the terms, so 6 minus 2 is 4. 4 plus 5 is 9. Right, so it's going to be here. 9 there, that's V. Another quadratic equation. Yeah, okay, so probably the easiest thing to do. We could think of factorizing it, I suppose. So it'd be factors of 15 that add together to give you 6. Well, 15 and 1 doesn't work. 3 and 5, that gives 8 or 2. So no good. Formula for solving quadratics: negative b plus or minus square root b squared is going to be 36k squared minus 4 times a times c. That's 15k squared. Divide all that by 2a, which is 2. Right, 6 divided by 2 is negative 3k plus or minus. Well, it'll be k squared. It's a common factor. 36 minus 4 Well, 2 times 15 is 30, so that'll be 60, right? 36 minus 60, the difference of those is 24, right? Square root 24, that's the square root of 4 times 6, I believe. So it'll be 2 times the square root of 6. So in other words, we can get the k and the 2 outside, and we get left with the square root of negative 6. Remember, there's a negative on this, over 2. That should have been divided by 2 here. So that's just equal to minus 3k plus or minus. Now the square root of negative 1 here is I. Let's try and write it like this. So it'll be the square root of 6 k I. Yep. So a is equal to negative 3, b is equal to 6. B is equal to 6. Yeah. This is a hint to polar form. So we could write z equals r e to the I theta. But actually, we want to take the cubed root. That's tricky because with complex numbers, you can take a cube root of something like I don't know. You could have some angle, and if you do it two more times, you should be able to get to the original angle. And there's usually multiple solutions for these things. It's like analogy of plus or minus square root, but this time we're doing a cube root, and so because you know 2 solutions, and this one will give you possibly 3. So that's just what you might think in the back of your head. Basically, because you can, go around a circle and split it into 3. So 1, 2, 3. That's the idea of the cube root. Starting from some vector and just wrapping around 3 times. So actually want to write this in polar form. Minus k to the 6i. So I is equal to 1 e. Well, let's draw it. There's I. What's the angle? Pi over 2. So e to the I, pi over 2. So let's just put that in there. And then we do the cube root of all that. So, sorry, it's better to write it like this. I don't want the negative. I guess I could, I don't know. It's k to the 6 times negative I. So negative I is, the angle here is 3 pi over 2, right? This angle here. So e to the 3 I times 3 pi over 2. But we've got to take the cube root of all that. Okay, so that's k to the 6 over 3, and then when you cube root that, you just divide by 3, so it'll be I times pi over 2. Alright, so it's k squared e to the I pi over 2. I guess you could call that the principal argument. but there's another solution. So we could factor that equation as x z minus k squared e to the I pi over 2 times another factor, and then times another factor, I guess. But two of these could be the same, so it could be that squared times the other one. You've got to have a z cubed somewhere there, right? Whatever that is. It's the other solution. I don't know what to call it. Let's call it A. How do we get that? So when we cube it, we want to end up with E. We want to end up down here, right, at minus I. So what I need to do is 1, 2, 3. So you take pi over 2 here, and you just go 1, 2, 3 times pi over 2. But there's another one. It could be well, I'm going to write it in a polar form. K squared e to the I theta. Now here, the theta 2, I'll call it the second solution. So what we want is when we cube it, like 3 times theta 2, it's got to be a solution to this thing here. So when we take 3 times it, it's got to be equal to so what I should have done here is just noted that's 3 pi over 2. It's the same as negative pi over 2 if you think about negative angles. Anyway, let's try it. Let me try writing this again. I think I had a better notation. Yeah, I want to go. I want to find solutions that are on the unit circle. So, but yeah, so it's possible that we could get a double solution, like double root, but I'll see if we may not do that. So let me get rid of that. Try a more systematic thing. So the idea is that we want 3 times our angle to be equal to the angle for argument for negative I, which is 3 pi over 2, right? But we can withstand any multiple of going once around the circle, 2 pi. As long as we remain in the on the unit circle, so we don't sort of repeat ourselves. We can go as many times around the circle as infinitely many solutions if you like, but in reality, most of them are the same. They're just repeated, and so right. So the general solution for some n will be, we'll divide by 3. So we can have a multiple of 2 pi over 3 up to the point where we go beyond 2 pi. So the first solution is called theta 0 because that will be n equals 0. It's actually a valid solution, so that'll be pi over 2. And we can check 3 theta naught equals 3 pi over 2, which is what we wanted. Okay, so the next solution could be n equals 1, so it would be that, now what's that? Cross multiply, so 3 plus 4 is 7. 7 pi over 6, right? What's a nice way to write that? Pi plus, it's 6 pi plus another 1/6 pi. Pi plus pi over 6. It's let's do a sketch of these things. So the first solution is 3 pi over 2. Pi over 2, 1, 2, 3. So it's sorry. First solution was pi over 2, so that's up here. That's theta 0. We can check like 1, 2, 3. Yeah, that gets us to negative I. And the second solution is pi plus pi over 6. So pi is 180 from here to here, and then 1/6 would be sort of somewhere here, 30 degrees out. That'd be theta 1. So we could check 3 times that, right? So it'd be 1, 2, 3. Wait a minute. Plus 3 pi's over 6. Well, that's pi over 2, so that gets us to minus I. Check for that. If you like the algebra check. I just checked it graphically in my head, but 3 theta 1 is 7 pi over 2, which is, okay, so that's 4 2's are out to 3 2's. It's 3 2's is 6 plus 1 pi over 2, right? You could also write, sorry, 3, yeah. It's 3 plus a half pi's. But you could write that as 2 pi plus 1.5. So the 2 pi kind of goes around the circle, and we get left with 3 2. So that checks out. And also this is less than 2 pi, so 7 over 6 is less than 2. So we can go up to 12 over 6. The 12 over 6 would be clocking it. So let's try one more. There should only be 3 solutions because it's a cubic. I suppose you know the idea that any polynomial in z to the n in complex numbers will have n solutions. Any rational polynomial, so rational coefficients and that sort of thing. Or actually any polynomial for complex numbers, any real number coefficients. Yeah, anyway, what am I doing? So this will be pi over 2 plus 2, so 4 pi over 3. Right, so cross multiply again, so that'll be 3 plus 8 is 11 pi over 6. So we can write that as 1 plus 1/6 pi, right? So that means it goes around pi 180 degrees plus a 6th. Oh, that's the same. That's equivalent to theta 1 mod 2 pi, right? So it's not an extra solution. So yes, there were 2 solutions that coincided on the unit circle. So there's just these 2 here, I believe. No, wait a minute. That can't be right. What am I saying? And I was getting confused with my fractions here. 6, 7, 8, 9, 10, 11, it's 5, right? So it's equal to 1 plus 5 over 6 pi. So that's 1, and then 5 pi over 6, so like 1, 2, 3, 4, 5. It'll be over here. that'll be pi over 6 in the middle here, so that'll be theta 2. It's different. After that, you can see we're going to clock it. So those will be your answers. Okay, so the roots will be z naught equals, what do we have, k squared e to the I pi over 2, k squared e to the 7 pi over 6, 7 there, and k squared e to the 11 pi over 6. 3 solutions. Prove there's no complex number, blah. My guess is that you want to use rectangular form for this and then come up with a contradiction like -1 equals +1 or something like that. So let's say that z equals x plus iy. That's any complex number can be written like that. And so the absolute value of z will just be x squared plus y squared, power of half, and I guess then okay, let's call this proposition P. Okay, so if the proposition P is true, then it should be the case that x squared plus y squared to a half minus x plus iy equals I, which would imply both ways, like if this is true, the other one is P is true, the statement P. Yeah, so I don't know, I guess that's a real number, right? So just keep it like that for now. Equals x plus 1 plus y plus 1 times I, right? Okay, so this would imply y must be equal to -1, which would imply put -1 into here, because there's no imaginary part of the left hand side equals 0, so that must be equal to the imaginary part of the right hand side here, so y plus 1 must be equal to 0. So that means x squared plus 1 to the power of half must be equal to x, right? I guess we could square both sides, right? So x squared plus 1 must be equal to x squared. And oh yeah, so, yeah, so subtract x squared off both sides, you got 1 equals 0. That's false. Therefore P is false. So there's no complex number, which is what we wanted to prove. You could say QED, quo erat demonstratum. It's a Latin for, which is what we wanted to prove or desired to prove or something, which is what there was to prove. Okay, just went to grab a cup of tea here, and They should definitely allow. Well, you can have drinks in the exams, can't you? Alrighty. Got this one here, complex number. Okay, so the trick would be to. Well, it's not obvious. Maybe you could do polar coordinates too, but since it's in rectangular coordinates, we just use what they've got given to us here, a plus b, and so we can just write down exactly what it is. And to make it nicer, we want to multiply by the complex conjugate upstairs and downstairs. So it's like multiplying by 1, doesn't change anything. So this will be, you know, similar. It's the conjugate there, so it's minus IB, and we'll multiply by the complex conjugate of the conjugate, and so therefore the top stairs will have a times I minus b times I squared, right? So that's a negative I squared is -1, so it'll be plus b, and then 3a so plus 3bi, and that both denominators here are going to be a squared plus b squared. So we could multiply by a squared plus b squared. So 1 times a squared plus b squared on the right hand side. Oh yeah, so just collect the real and imaginary parts together. So it'll be plus a plus 3b, right? On the right hand side, a and b are real numbers, sort of plus 0 times the imaginary number, right? So we equate the real and imaginary parts separately, so we must have 3a plus b equal to a squared plus b squared, but don't know either a or b yet, so let's just call that equation 1. Simultaneous equations, essentially. So the other one is simple because it's a plus 3b equals 0, right? Treacherous minus signs here. I don't know. Better make sure I got the minus signs right. Anyway, so that would be easy to solve. That's just a equals -3b. So we can substitute, put 2 back into the equation 1. So 3a would be -9b plus b, and then a squared would be 9b squared. Okay, good. So that's -8b would be equal to 10b squared, and we just divide by b's on both sides, right? So it'll be b equals negative, and divide by 10 as well. -8 over 10, which is negative. Both are divisible by 2, so 4 over 5. And therefore a would be equal to positive 12 over 5. Good. You could check that on your calculator if it does complex stuff. I think I might have checked this before. Okay, I might have gone wrong as well. Previously I did it wrongly. Because previously I think I did 9 minus b squared. I somehow mistook the plus for a minus. I don't know how I did that, but that can happen in an exam, right? So basically, I might just define this thing here. Z equals 12 over 5 minus 4 over 5 times I. Now, so I divided by Z plus 3 divided by conjugate z. We want that to be equal to 1. That's a mess, so we want to simplify that. Yeah, it's equal to 1. Not sure if you'd be able to do that on your electronic calculators, but... Oh, okay. Is that it then? Alright, we finished. Let's see how long that took. Again, if it took you longer, I don't think you should worry, but in the exam situation you should write a letter to the New Zealand Qualifications Authority and tell them that you just need a bit more time in the exams. That would be my political statement. Okay, see you on the next video.